So what is quantum tunneling? Imagine you're rolling a ball up a hill. If the ball doesn't have enough energy, it can't get over the hill. It rolls back down. That's how classical physics works. But in quantum mechanics, particles like electrons or protons don't behave like balls. They're governed by something called the wave-particle duality. Instead of being in one specific place, they exist as probability waves, meaning they have a chance of being here, there, or even on the other side of the hill. In quantum mechanics, particles can't tunnel through barriers they shouldn't be able to cross if we only consider their energy. This happens because their probability wave extends beyond the barrier. There's a tiny chance the particle might appear on the other side. And that's exactly what happens. This doesn't mean the particle smashes through, it's like it teleports, but in a probabilistic way. Quantum tunneling isn't just theoretical, it's all around us. Here are 3 key examples. In the sun, nuclear fusion needs protons to collide. Their positive charges repel each other, so classically, fusion shouldn't happen. But thanks to quantum tunneling, protons can bypass this energy barrier and fuse, producing the energy that powers our solar system. Quantum tunneling is what makes semiconductors and transistors work. These are the backbone of all modern electronics, from smartphones to computers. Quantum tunneling is used in scanning tunneling microscopes to observe individual atoms, revolutionizing nanotechnology. Quantum tunneling is fascinating because it breaks the rules of classical physics. It's a vivid example of how the universe operates on a scale we can barely comprehend. It's not magic, it's quantum mechanics. So, the next time you see sunlight or use your smartphone, remember that quantum tunneling is quietly working in the background, making it all possible. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more mind-blowing science content.